Abstract. Reliability for businesses begins with management and their communication about the need for a failure-free environment. This mobilizes actions to preserve operable systems and processes. Reliability considers the cost of alternatives to prevent or mitigate failures, requiring knowledge about times to failure and failure modes found by reliability technology. Justifications for reliability improvements necessitate knowing when things fail. 2. How things fail. 3. Conversions of failures into time and money. Reliability engineering principles define when and how things fail, providing facts for lifecycle cost comparisons. This aids in deciding the lowest long-term cost of ownership driven by net present value for converting hardware issues and alternatives into money issues. Several short examples illustrate the methodology. Reliability. Definition. Reliability is the probability that a component, system, or process will function without failure for a specified length of time under specified conditions. Real-world considerations. In reality, everything fails either due to events or aging. Perfection exists only in a fantasy world, hence we must continually maintain processes and equipment to prevent disorder and failures, which requires spending time and resources. Key concepts. Entropy. Natural law of entropy expresses the lowest energy state as a failure. Probability and costs. Quantifying reliability involves understanding why, how often, and the costs of failures, bound to the physics of failure mechanisms. Reliability prediction is probabilistic due to the often unknown potential failures. Distinction. Reliability is not the same as availability. Reliability is about the probability of a failure-free interval, whereas availability is the percent of time the system is ready for use. Risk assessment. Reliability connects money with failures using the equation 2 equals text probability of failure during a specified time interval and under specific conditions, times of the failure event. Risks always exist and are never zero. The affordability of risk is a business decision, often based on acceptable loss thresholds like $10,000 or $100,000. Planning for success and rejecting abnormal risks are crucial. In the end, reliability is all about money for industrial businesses. What does your reliability policy say? Management presents important issues to the organization with policy statements. Policies define specific areas of concern and indicate the desired outcome. They increase decisiveness by removing uncertainty about the action required to meet objectives. Policy statements communicate information to the staff in general terms for detailed implementation by procedures in a consistent fashion through individual acceptance and commitment. Good policies reduce inefficiency, counterproductivity, inappropriate risk-taking, and conflicts over requirements, preventing implementation voids. Modern organizations have safety, quality, and environmental policies, each calling for 0 lost time injuries, 0 defective shipments, and 0 environmental releases. Essentially, reliability statements. Reliability issues for processes and equipment also need clear policy statements to avoid fuzzy interpretations. A suggested reliability policy could be, we will build and maintain an economical and failure-free process which will operate for 5 years between planned outages. Management must set the reliability policy, driving procedures and rules. Policies must integrate safety, quality, risk, and financial requirements, and be understandable to all, originating from top management for credibility and purpose. Management's role in reliability extends to the design and maintenance of equipment and systems. It must set clear requirements so everyone understands the objective, providing a failure-free environment for the process, despite potential losses of components and equipment. Management must strategize, considering the costs of failures and establishing procedures to communicate these costs. The cost of failures, even though a human life is priceless, needs quantification for business trade-offs, often guided by assumed values for communication purposes, such as the cost of fluid spills or civil penalties under environmental laws. Assumed values. Examples of assumed values for failure events include spill loss of 1 gallon of undesirable fluids equals $500. Spill loss of 100 gallons of undesirable fluids equals $3,000. Spill loss of 1,000 gallons of undesirable fluids equals 250,000. Spill loss of 10,000 gallons of undesirable fluids equals 1,900,000. Spill loss of 100,000 gallons of undesirable fluids equals 20,000. Violation of Clean Waters Act civil. Penalties: $25,000 per day, or $1,000 per barrel of spilled material, $3,000 for gross negligence. Calculated values for failure events can be accidental death of one person. Probability of failure equals 10 to the minus 4 equals $2,500, multiplied by 4 for disablement. Accidental death of 10 people. Probability of failure equals 10/6, $250,000, multiplied by 4 for disablement. These values serve for communication purposes only and are not meant as guidance for legal or insensitive viewpoints. The purpose of these values is to translate humanitarian and violation issues into monetary terms, facilitating business decisions. The probability of failure is expressed in reliability terms, making discussions about human risks less emotional and more business-focused. Including failure details and procedures helps convert failure issues into monetary terms, guiding the organization to make logical and unemotional decisions about reliability matters. The probability of failure for one person at 10 minus 4 is equivalent to reliability equals 0.9999 and 10/6 to reliability equals 0.9999. Thus, reliability discussions are more palatable than probabilities for human failure. Human risk values are typically set lower than other business risks. Calculated values. Examples of calculated values for failure events include accidental death of one person. Probability of failure equals 10 to the minus 4 equals $2,500,000, multiplied by 4 for disablement. Accidental death of 10 people. Probability of failure equals 10/6, $250,000, multiplied by 4 for disablement. These values serve to communicate the monetary impact of failure events and are not meant as guidance for legal or insensitive viewpoints. They aim to facilitate business decisions by translating failure impacts into financial terms. The probability of failure is expressed in reliability terms, making discussions about human risks less emotional and more business-focused. Assumed values only for communication purposes. Assumed values for communication purposes help provide guidelines for failure events or failure avoidance, including lists of applicable specifications and regulations for compliance audits. If the events occur in a sensitive area, increase the cost by a factor of 5. If the events occur in a benign environment, reduce the cost by a factor of 5. These numbers are quantified to convert humanitarian and violation issues into monetary terms so business trade-off decisions can be made. They are not intended to be guidance values for lawyers, nor represent callous viewpoints about the value of human life. Including failure details and procedures helps convert failure issues into monetary terms, guiding the organization to make logical and unemotional decisions about reliability matters. The probability of failure for one person at 10 to the minus 4 is equivalent to reliability equals 0.9999, and 10^6 to reliability equals 0.999999. Thus, reliability discussions are more palatable than probabilities for human failure. Human risk values are typically set lower than other business risks. Reliability models. Reliability engineers discuss issues with reliability and availability models with a challenge balanced against the capacity to handle adverse conditions. Systems and processes have inherent capacities to handle challenges, with success occurring when the challenge is less than the capacity, and failure occurring otherwise. Failure mechanisms are physical processes attacking these models. Typical reliability models include 1. Stress strength models. Stress represents the aggregation of challenges and external conditions, while strength represents the variability of conditions affecting the system's capacity to repel the challenges. 2. Damage endurance models. Similar to stress strength models, but the stress causes irreversible and cumulative damages, such as corrosion, wear, embrittlement, and fatigue. Failure occurs when cumulative damage exceeds the component or system's capacity. Challenge response models. Failures occur due to critical events rather than typical situations like the passage of time or cycles. 4. Tolerance requirements models. Failures happen when performance characteristics fall outside predetermined limits, with gradual degradation occurring based on use or time. Mechanical failure mechanisms are classified into stress-induced failures, caused by permanent or temporary stresses, categorized by brittle fracture, buckling, yield, impact, ductile fracture, or elastic deformation. Strength-reduced failures, led directly or indirectly to failure, categorized by wear, corrosion, cracking, diffusion, creep, radiation damage, or fretting. Stress-increased failures, increase the applied stress, categorized by fatigue, radiation, thermal shock, impact, and fretting. Electrical failure mechanisms are divided into electrical stress mechanisms, result from voltage levels that damage devices or degrade characteristics, categorized by human error, uncontrolled currents, voltages, localized heating, melting, and latent damage. Intrinsic failure mechanisms, related to the electrical electronic element, categorized by issues like gate oxide breakdown, ionic contamination, surface charge spreading, and hot electrons. Extrinsic failure mechanisms, external problems related to device issues, interconnections, and undesirable environmental conditions. Failures can be accelerated by unexpected combinations of events, often triggered by specific situations acting as catalysts. Traditional techniques for coping with challenges include making components, systems, and processes very strong and keeping loads very low. Reliability engineering versus maintenance engineering. Reliability engineering is strategic, focused on predicting and avoiding failures, whereas maintenance engineering is tactical, concerned with quickly restoring failures to an operational condition. Changing job titles to include reliability without changing tools and approaches results in style without substance, as reliability and maintenance engineering are fundamentally different. Both disciplines have overlapping territories and must understand each other's roles, responsibilities, and tools. Reliability is akin to the fire marshal, predicting failures and reducing costs with long-range tools, while maintenance is like the firefighter, addressing failures as they occur. Preventing failures costs money for equipment, procedures, and nurturing the system, just as repairing failures does. Both activities are ruled by money, and improvement projects require engineering details converted into costs for annual time buckets to define cash outflows accurately. Many companies use 10-year to 20-year intervals for study periods. Engineering must predict failures for accurate pricing in net present value, NPV worksheets, providing information on failure modes and severities. Costs must include gross margin losses from production outages, especially for continuous process operations where production is sold out. Reliability engineering tools. Reliability involves the sweet absence of failures, quantified by measuring the sour presence of failures, which occur naturally due to the laws of physics and entropy. Effective reliability programs require detailed knowledge of various tools and their industrial applications. These tools focus on fact-based issues rather than subjective assessments. Key reliability engineering tools include mean time between failures, MTBF indices, total productive maintenance, TPM, and reliability principles. Preparing reliability data for analysis, decision trees merging reliability and costs, Weibull, normal, and log normal probability plots, corrective action for Weibull failure, models and Monte Carlo simulations, Pareto distributions for vital problems, fault tree analysis, design review, load strength interactions, software reliability tools, sudden death and simultaneous testing, failure recording, analysis, and corrective action, failure mode effect analysis, FMEA, bathtub curves for modes of failure, availability, maintainability, capability assessments, critical items significantly affecting safety costs, quality function deployment, mechanical components testing for interactions, electronic devices screening and derating, reliability testing strategies, accelerated testing, contracting for reliability, reliability growth models and displays, cost of unreliability, reliability policies and specifications, reliability audits. Management's role in reliability improvements. Failures fall into 3 regimes: infant mortality, chance failures, and wear-out failures. Human errors are usually chance failures, while infant mortality and old age wear-out failures are superimposed on chance failures, forming the typical bathtub failure curve. This idealized curve is seldom observed for equipment but common for human failures. Analyzing equipment failures requires Weibull analysis of small samples, with software making the task easier. Simple arithmetic techniques like MTBF, or mean time to failure, MTTF, are often used as reliability precursors. Most reliability tools are practical engineering tools, often learned through continuing education rather than formal university courses. Lifecycle costs. Lifecycle costs, CC, refer to all costs associated with acquisition and sustaining costs for ownership of a product or system over its full life. The usual figure of merit is net present value, NPV. NPV is a financial tool for evaluating economic value added. It is the present value of an investment's future net cash flows minus the initial investment for a given discount rate hurdle. The present values for each year of the project are summed for the net present value. Net cash flows are a measure of a company's financial health. Discount rates are the interest rates used in discounting future cash flows. The discount rates include the cost of money, bank and company administration costs, and risk costs for the lender. They are always larger than federal bank rates. For an entire project, the lifecycle cost number requires a positive NPV. Bigger positive NPVs are better. Project elements cannot easily show profit savings for each equipment component, and decisions are made in selecting equipment based on the least negative NPV, where smaller negative NPV is better criteria. Many improvement projects will have positive NPV along with internal rates of return, IRR. As a second criterion, insisting on higher rates of returns on many small projects that must jump a very high hurdle to hold down the expenditure for capital money, particularly if the company lacks access to financial money for improvements. All LCC tasks require comparisons of alternatives. Note the word alternatives is plural. In every LCC task, conflicting issues are obvious. Project engineers want to minimize capital expenditures. Accounting wants to maximize NPV. Shareholders want to maximize dividends, share price. Production wants to maximize uptime hours. Maintenance engineers want to minimize repair hours. Reliability engineers want to avoid failures. All parties want someone else to put the numbers together to justify their love affair with the project or equipment, which justifies their decisions. Business is about time, money, and alternatives. Time and money are both in short supply. A single alternative is without choice and unwise because the default position is to do nothing. The LCC concept merges time and money together to arrive at a single indicator called NPV for each alternative. NPV numbers prioritize the projects to select the winner from the alternatives, so you buy right rather than only buying cheap. Techniques used for finding LCC are available in training formats. Technical papers are available for download from the internet as PDF files. Making the lifecycle cost calculations is easy when you have the data. The difficult effort is how to resolve the chicken or egg dilemma for finding failure data, maintenance data, and other details involved in the sustaining cost, as the acquisition cost is usually the only accurate number you have, as it is a quotation. You need reliability engineering details to find when things die. Failure data and repair time data can be converted into statistical format using software for use in reliability calculations. Few individuals claim knowledge of sustaining cost facts until someone else puts numbers on the table. Then the critics are numerous for correcting the proposed numbers. Follow the scientific method. Build a hypothesis for failures and their cost, and then test the hypothesis. When in doubt about the failure data or cost, make an estimate and test the estimate for validity. Much data needed for LCC comes from operating costs, including electricity, etc., and maintenance records which show times between failure and repair times. These details are often associated with the field of reliability and maintainability with a direct relationship for finding lower lifecycle costs. The cost details should also include costs for lost gross margin for outages of systems when it is appropriate. Some of the failure data is from simple arithmetic calculations, and other data follows the preferred method from databases. Conditions for installation, operation, and maintenance influence both failures and failure costs, which are susceptible to equipment grades for changing the financial performance. Often simulations, using random numbers, are required to find cost variability for different equipment grades. You can build simple, low-cost models using software available from the internet, which is useful for driving lifecycle cost decisions. The reason for building reliability models is to find where failure cost is occurring and to search for the lowest long-term cost of ownership, where system details, when priced out, provide a clear leading alternative for solving the problems. The reliability models show what's affordable and the less desirable alternatives. Reliability models, using actual failure data and repair times, give system availability, reliability, maintainability, and other operating system details which allow construction of costs and trade-offs. A clear definition of failure is important for reliability decisions and the data acquired. If you do not have data collection systems for your failures, you will seldom make substantial improvements in the reliability of your systems. Reliability models provide evidence for trade-off boxes. Engineers need graphics for understanding what's happening to their systems. The trade-off box has lifecycle cost on the vertical axis and effectiveness on the horizontal axis. Effectiveness is the product of availability, reliability, maintainability, and capability of the system to perform. Complex items become simple when you see the results. The left hand symbolizes too many failures and the right hand symbolizes too much equipment. The sweet spot lies between the extremes. What most companies need is the money and control of risk. They rarely need perfect solutions. Lifecycle cost helps provide the answers when driven by the tools of reliability engineering. When you have concepts and features on a product or process that generate value, the value must be quantified for inclusion in the lifecycle cost model. Summary. A reliability policy focuses the organization toward a failure-free environment to meet management objectives for the business. Reliability engineering tools predict failures and risks associated with certain actions. Details from the reliability analysis go into lifecycle cost models for merging engineering details into a format considering the time value of money. Lifecycle concepts rely heavily on reliability and maintainability technology issues to convert ideas into hard engineering facts, which convert issues into monetary values for making trade-off decisions about risks. The first cost for procurement is not the last cost. Procurement cost may represent only a small fraction of the total cost during the life of an item, and in other cases, it may be a large portion of the total lifecycle costs. General rules of thumb have much variance. The engineering facts must be converted into financial details of NPV and IRR with a selection of the best alternative from several courses of action. The decisions you make up front will be with you for many years, so it's important to justify risks and improvements using the best tools available. Without reliability details about failures, NPV is difficult to calculate for making correct business decisions about trade-offs with failure avoidance for reliability as a business focus. If your owners, customers, or the general public are unhappy about the reliability of your systems, improvements must be made. That is a call for change. To get change, you must make a change. If improvements are not voluntary and community outrage is high, trailing legislation will surely follow in ways seldom to your advantage. Unreliability must be quantified and resolved quickly for business purposes. Occasionally, reliability begins at low levels in the organization with long incubation times before recognizable progress is recorded. However, in private enterprise, high system reliability is best achieved top-down with policy statements to quickly put the organization to work for reaching a target in reasonable timeframes.